So we're going to start talking about binary trees. So a binary tree is a self-sorting tree data structure. Every time we add an element to the tree, it automatically positions itself in the proper location within the tree. Okay? So, high level is that. Let's talk about this in a little more detail. Let me flip back. Go here?
No.
Right here?
Yes, please.
Now here.
Thank you.
Good?
Okay.
All right, so as an example, let's say we started off a binary tree and the top node was a 5. Okay? Initially, a tree is just a root node. That's a legal tree. Okay? 5. Now, we're going to add another value. So let's say we're going to add a 3. All right, now, when we go to add this 3 onto the tree, should a 3 come before a 5 or after a 5? It should come before a 5. So as we drop down here, we're going to add it as the left child of this guy. Because, well, we're going to say everything to the left of a node is smaller than it. Everything to the right of a node is larger than or equal to it. Okay? You can also say everything to the left is less than or equal to, everything to the right is greater. You can choose which side of it. Now we're going to add a 2. Should a 2 go on the left or the right of a 5? Left. Should a 2 go on the left or the right of a 3? Left. Add a 4. Should a 4 go on the left or the right of a 5?
Left.
Should a 4 go on the left or the right of a 3? Right. Should a 6 go on the left or the right of a 5?
Right.
Right. And these really should be spread out more in this, just so we don't confuse that this guy's part of this tree. Make sense? Okay, now, we have a couple of ways of traversing a binary tree. Your actual homework assignment is going to be write the various traversal methods for it. In here, we'll write a binary tree. We'll write the structure for the binary tree. Then you're going to have to traverse it. So let's talk about those traversals while we're discussing them right now. Tree traversals. We have in order and post order. Let's talk about those two first. In order means we start at the root of the tree and we visit the node that we're currently looking at first, then the child nodes. Okay? In order says we visit the node we're interested in first, then its left child, then its right child. Then this guy, his left child, his right child. Okay, we're visiting them in order. An in-order search, an in-order traversal is used for what's called a breadth-first search of generic tree structures. Breadth first means we check this row, then we check this row, then we check this row, so on and so forth. Go ahead.
Every element has just 2 children, right?
Correct. In a binary tree, maximum of 2.
Could be 1.
Could be 1.
Could be 0.
Well, like for instance, this guy has 0 children. This guy has 2 children. This guy has 2 children. This guy has 1 child. Yep, but a maximum of 2. Maximum of 2 for a binary tree. All right, so visiting nodes in order is used for something called a breadth-first search. Okay? Typically, these would not apply to binary trees. So when we're talking about tree traversals, notice I haven't said binary tree traversals. I've generically said tree traversals. Okay? So this kind of goes back to what we were talking about with linked lists, how whether it's a singly linked list, doubly linked list, a list that acts like a stack, a list that acts like a queue, there's generic ways we can traverse it. You start at the head, you walk towards the tail, you start at the tail, you walk towards the head, that type of stuff. You traverse it one node at a time. Similarly, there's generic ways we can traverse trees. One of them is visiting it in order, another one is visiting it in post order. Post order says, so we're going to visit the 1, bounce back up, now we'll visit the 2, bounce back up, visit the 4, then visit the 3. So we visit the parent after we visited the children. Okay? So post order, we visit the parent after we visit the children. In order, or pre-order you could say, we visit the parent first, then visit the children. Yep. Depth first would be, all right, let me put these various vocabulary words in here. Depth first says we go all the way down, then bounce back up. Okay, so a depth first search would use post order. So in order is for a breadth first search. Post order is for a depth first search. Okay, so if you're actually searching for a value in a tree, you can choose whether to do a breadth first or a depth first search by either visiting the nodes in order or visiting them in post order. So what I want to do here, just as an example, and pay attention to this because it's the stuff you'll be doing for your homework. If we're going to visit this tree in order, in what order will we visit those nodes?
Five, 3, 6, 2, 4.
Okay, make sense? Okay, so that's in order. Post order.
1, 2, 4, 3, 6, 5. 1, 2, 4, 3, 6, 5.
Like that? Okay. Now, how would we visit these nodes? This deals with binary trees specifically. If we were to, since this is a binary tree, which is self-sorted, if I wanted to display the contents of a binary tree, we probably want to show the numbers in the tree in order. Not necessarily visit them in order, but display them in order. Where is the smallest value in our tree here? Bottom left. This is always going to be the absolute smallest value in the binary tree. Where will the largest value be?
Bottom right.
Bottom right would be the largest value. That make sense? Okay? So in this particular case, bottom right is a 6. If we were to add a 9, 9 goes to the right of 5, 9 goes to the right of 6. So the biggest value should be bottom right, smallest value should be bottom left, everything else is in the middle. So how would we visit the nodes if we wanted to display it in order? A 1, bounce up to a 2. Now, what if there was a right child here?
Then you would bounce
One,
over
you mean in
two.
order or what's up?
Neither.
Okay.
Yeah, I'm not talking about either of these guys. I'm talking about if we wanted to display a binary tree. So I'm adding another node here. So a 2. 2 goes to the left of a 5. It goes to the left of a 3. And let's say that because it's greater than or equal to 2, it's going to go to the right of the 2.
Right. So you would go left, right, then up.
Okay, so I'm going to drop down. I'm going to say, here's my smallest value. Where's the next smallest value?
2.
The left.
Which 2? This one or this one?
To the right of it.
No, the balance.
The parent.
Yes.
The parent.
Why?
This value is at least as big, if not bigger than the parent.
Oh, yeah, because it falls to the right.
That makes sense?
Oh,
So we visit this guy first, then get the parent, then get
The line.
the other child, then bounce back up, get the parent, get the other child, then bounce back up,
so,
get the parent, then get the other child.
question. So when you bounce back up from the right side, are we listing that same 2 again? Or are we just going back to go up?
You're remembering you visited this already.
Okay.
So the order we'd visit these nodes, if I'm just going to tack them here, is we go here,
So,
here, 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 here.
okay.
That's the order we would need to visit them in order to display the contents of a binary tree in order. Does that make sense? Taking advantage of how binary trees work. All right. So your homework is going to deal with traversing our, in this case, it's going to be a binary tree, but traversing it in a breadth first search, in a depth first search, as well as an in order search. Not to be confused with visiting the nodes in order. Okay, so in order is what we just did, where the printout should be 1, 2, 2, 3, 4, 5, 6 in order. Okay, depth first gave us the 1, 2, 4, 3, 6, 5. Breadth first gave us 5, 3, 6, 2, 4, 1. Make sense? Okay, so those are the 3 different things you'll be doing. And I'm going to actually go in while we're still talking about them. Let me jump in and, because I actually changed up the homework assignment a little bit here. Given our binary tree implementation below, so we'll attach that when we're done. Write methods to visit the nodes in a depth first search order, a breadth first search order, and an in order search order. That make sense? Okay. And then at the end, I'll put our project in there. So that'll be your homework assignment. Historically, we took the crawler one more level, but we're actually, because you negotiated, we're not meeting next week. Is that correct?
Yeah.
Okay, because of Thanksgiving? Okay, but you will have an assignment.
Yeah.
Okay, so what I'll do is for next week, I'll post an assignment that builds off of this one. Okay, because otherwise the crawler is ended this week and started something new next week, binary trees, so you get it. All right, so there will be a new assignment that I will put up by Wednesday next week. This is probably easier than the crawler would have been. Binary trees aren't that difficult.
You sure? Because you seriously sat there and thought up a hard assignment on purpose.
No, this is actually an easy assignment. I just wanted to know what you needed to do, what you had to do for it. I could make you write the binary tree too.
No. Just go ahead and we're gonna go ahead and do this.
Binary trees are actually really easy.
Yeah, I'm just.
So it's not posted.
It will be. I just have to unlock it. Yeah. I won't unlock it yet. That way I don't forget to put the zipped file of the code.
Question.
That way, worst that happens, you scream at me and say, "Where's the homework?" And then I'll remember I have to zip up the code. But I usually do it right at the end of class. Yes.
Oh, can you replay again what you said about the? Never mind.
What do you want me to do?
Never mind. We good. Yeah, we good. Go ahead. You may resume.
All right, well, here. Maybe this is what you're looking for. Breadth first. Depth first.
And then the in order is the 1, 2, 2, 3.
Correct.
4, 3.
In order. In order is how you count. 1, 2, 2, 3, 4, 5, 6.
Didn't we go back to the? Oh no.
Oh, and these are actually missing some numbers because we added this 2 in there. So here, let me. Now we're legit again. So notice in order visits them literally in order. 1, 2, 3, 4, 5, 6.
Okay.
Depth first deals with whether we visit the parent first or visit the parent after. Make sense? Okay. So depth first and breadth first have little to do with binary trees. Little to do with binary trees. They just are a tree searching algorithm. So we have a tree, might as well traverse it in some way. Okay, so let's go write our binary tree. I'll go ahead and create a new project for this. Java project 537 fall 2014 binary tree. Good enough. And we'll create our class driver. Yeah, if we're efficient here, we might get out shortly after 9 again.
Yay.
Never know.
I like the sound of that.
I babble sometimes, though.
I'll keep you.
It'll probably be close to 10.
I'll keep you on track. We got this.
We got this. All right. Public static void.
We just didn't add it in there when we created the class.
Oh, use their built-in thing?
Yeah.
I don't like using built-in stuff.
Okay. Why not?
I've been programming for a really long time. You know how people get kind of set in their ways? I don't like using built-in stuff very much.
Interesting.
Yeah,
Wouldn't it make your life so much easier?
I type that pretty easily. I know what you mean. And really, maybe I think it comes from teaching.
Oh, okay.
There is so much value in being able to just do that over and over again from a programmer's perspective and not have to always go back to notes to even start a program.
I get what
So
you're saying, yeah.
I'm always trying to exemplify that for students, so I end up just doing it for myself as well. I also typically like writing, because I'm constantly coding in front of groups, I like writing code that's very explicit as opposed to code that maybe is,
Ambiguous.
well, the most compartmentalized. There's probably better ways of encapsulating your code in objects than I typically do in front of a group, but it's harder to follow. And if they're trying to learn something new, take them the way that has less traffic. If you're teaching somebody how to get somewhere. Okay, so I always just do a little quick little system without that println. I misspelled it. Okay, so it worked. So we know we have a working project now. So we got to go back. Go ahead. Sorry.
That's fine.
You were just babbling?
No, because you told us we have to, to remember we have quiz about Hello World.
Was that today?
No, not today. 3 weeks ago. So.
I hate you people.
You know, I actually remembered that earlier today, but I was going to keep my mouth shut, unlike some people.
So it's giving you all zeros on it. It's the way
No, give him a 0 on it
Wait.
since he opened his mouth.
it works. All right, so for our tree, we're going to have a class called binary tree. And binary tree is going to have a private node called root. All right, so all trees have a root node. All right, now if we think about a binary tree, so this is our tree, the binary tree itself has a single root node. Each node knows about, at most, 2 nodes. Okay, so let's look at what a node is. This is a node specific to binary trees. Okay, a node knows about its value, what value it holds, also sometimes called payload. A node knows about its left child and its right child. Okay?
They call it a payload?
That's the thing it holds, payload. Yeah.
Okay.
Payload's what you'd see in data.
It contains like 3 things: value, left child, right child.
Correct. Yeah, and the picture shows this, right? There's the node. It has a value of 3. Here's a link to its left child. Here's a link to its right child. Pointer to its left and right child. Okay, so that's our node. Fairly simple. So I'll go ahead and create a node class real quick. Yeah. Rather rewrite it. Otherwise you spend all your time trying to take stuff out and you're forgetting how a certain thing works and the code's broken. Might as well just write it from scratch.
You do it the easy way. You just highlight everything and hit delete.
Right. That's right. Oh.
Private node.
Private int value. And private node left child. Private node right child. So when we create a node, we can have it bring in a value. And then we can say this dot left child is equal to null. This dot right child is equal to null.
Why you said null is equal to null?
Because a node, when it first comes into existence,
It doesn't have any children.
yeah, no children.
Oh, okay.
So here's that's our simplest tree. This is a dude with a value, has no children. Okay. So our binary tree has our root node. And what we'll do is we're going to have our constructor for our binary tree. That just sets this dot root equal to null. Okay, then we want to be able to add a value, and I need to give it a... Okay, add a value to our binary tree. So, for example, we had our tree originally. Put my Legos over here. And we brought in a 3. We're adding a 3 to this tree, right? So to add the 3 to this tree, we first had to ask ourselves, well, let's start off with this. Initially, we had the empty tree. We added the 5. Since the root node is null, we just put the 5 there. That's the simple case, right? All right, so if this dot root is equal to null, then this dot root is equal to a new node with value. Else, got to place it. Okay? So
if we're going to have the 3, it's going to be the place of 5 as a root.
what do you want to add next?
Let's say 3.
Okay, so 3, if we added 3 to the empty list, it would go right there. Okay, yep. Then what do you want to add?
I'm saying 5 is the first one,
It's the
and
root.
we get it's the root, and we're gonna add 3. It goes in the left, right?
Correct. It goes in the left, right. Yep, goes into the left, right.
Okay.
So we go to add this to our tree. Since the root node is not null, we ask, should this guy go to the left or go to the right of this guy?
But first it has to have a value, correct?
Well, it has a value, 3.
No, I mean, if we're like creating a new node for the child, then just like we had to add a value to the root node, we have to add a value to the child first.
Right, so initially the tree's empty.
Right.
I'm going to pass in the number 5. I'm going to notice that the root node is empty, so I'm going to create a brand new node holding the value 5 and point root to it. That's what I did right here.
Right.
Root node's null, so now make root point to the new node created with our integer value.
So now when you're doing child,
Now if I'm adding a 3, we'll call that same add method. The root node is not null, so now we need to decide where we're going to add it. So we need to look at the value of this node
right.
and decide which child it goes into.
That's what I was asking about is that node, the new child node, is it still null right now, even because we haven't added a value to
Oh, well, it is null because we haven't even created a node yet. Right now we have a primitive type val, or value. We haven't actually added, we haven't turned it into a node yet.
Okay.
So we have a root node called root. That is our top level.
Right.
And remember, we're in binary tree here. So if we aren't just by default putting this guy at the top level, he's instead going to go somewhere in the tree. Make sense? All right. So what we're going to do is we're going to add the ability into node. Because the node class knows about its value, it knows about its left child, it knows about its right child. Okay? So in node, we're going to add a method called add. That's going to take a value. Now, if I'm a node, I already know that I have a value. Correct? So this guy isn't overwriting me. What I'm really deciding as a node is which of my children is going to take care of this guy. Right? Okay. So if value is less than, do we decide the left was going to be less than and the right's going to be greater than or equal to?
Right.
Is that what we decided?
Yeah.
Okay. So if value is less than this dot value, so if the value that was just passed in is less than the value of this particular node,
Left child.
okay, then that's left child, else right child. Now, if we're adding to the left child, what if we already have a left child?
You have to check
Then
again.
you do another-
Tell our left child to add this dude. Following this? Okay, so if this dot left child is equal to null, our search is over. So we'll set this dot left child equal to a new node value. And we're done. Else,
Call the method.
this dot left child dot add value. Tell our left child to deal with it. I don't know what to do with this guy. You deal with him. I know he goes on your side of the court. That makes sense? Similarly, if this dot right child is equal to null, then this dot right child is equal to a new node value. Else, this dot right child add value. Make sense? So, if it's not going to go into the root node, it's going to go somewhere in the tree, so we'll just say this dot root dot add value. That's it.
Oh wait, which add method is it calling? The one that's in or the one
Roots a node. It's calling roots
duh.
add method.
Gotcha.
That's a binary tree.
That's it.
That's it. It's the whole binary tree. So once again, the complexity is built into the data structure itself, not the implementation of it. All right. So what I'm going to do, let's see, and I can't display it without doing some of your homework. There. This will work okay. So we're going to create a binary tree. B tree is equal to a new binary tree. Then we'll say B tree dot add there's our 5. We just have the 5 list. Then we'll say B tree dot add 3 let's do a bunch of these. So we'll have 2 5s. If on the right, it's greater than or equal to, right?
Oh my goodness.
Okay. What I'll do is I'm going to say find smallest, find largest. We're going to write 2 mini methods. Okay. So we're going to have public int get smallest, and then we'll have public int get largest. So where's the smallest value in a binary tree?
The bottom.
Bottom left. Okay, so we need to keep walking as long as there's still a left child. Okay, so if this dot root is equal to null, then probably throw, actually, you know, just for this example, let's just assume we would never ask this for something of
No.
something with nothing in it. So we're going to say node cur node is equal to this dot root while cur node dot, we need to be able to get at its left and right child. So we need to build into node public node get left child. And public node get right child. All right, so we expose those couple of variables to our end user now. In binary tree, while cur node dot get left child is not equal to null, as long as it still has a left child, then cur node is equal to cur node dot get left child. Ultimately, we want to return cur node dot get value, which we haven't written yet. So we'll go into cur node. We'll give it one more method here, public int get value that returns this dot value as an int. So cur node, this will return cur node dot get value. That should be our smallest. Similarly, as long as we do have a right child, we'll keep getting the right child. And this, when we exit out of this, this means that we're at the final right child. And we'll go ahead and return cur_node.getValue. Back out here in driver, if we say system.out.println btree.getSmallest, that should give us a 0. And get largest should give us a 13. So there's our 0 and our 13. Make sense? All right, so probably enough information there to convince us that the stuff got added the right way. If it didn't, you guys can fix it as part of your homework assignment. But I feel pretty good it's right. But interestingly, isn't it kind of neat how simple binary trees actually are to write? There's not a lot to them. It just happens to be that the way they function is always adding stuff in order. Now, the one thing we do need to be careful about, though, is, and we'll talk about this is going to be related to your homework assignment for next week, is balancing a tree. People use binary trees as search trees, holding pieces of information. So for instance, database programs like Oracle and stuff like that are going to use, and this could actually help you also in the report for this week, which asks you to look into real-world applications of binary trees. But for example, a place like Oracle, which runs a database management system, they very well might use binary trees, amongst other things, as a way of storing their data in a sorted way to make it fast to run queries on the data. So given that, one thing that's important is that a tree is balanced. Depending on the order that you entered the information, so I can ask it this way. If I took these exact same numbers and I added them to my tree in a different order, would my tree look different? It would. Okay. Ultimately, the smallest value would be in the far left. Ultimately, the largest value would be in the far right. But at a glance, the tree might look very different. That makes sense? And you'll see that when you do your breadth first display of the data in the tree. You'll see that if you display a tree, it does matter the order in which you put the stuff in there. So if you get a tree that's very left heavy or very right heavy, where to search for a piece of information, you have to go down 50 levels over here, and there's only 2 levels over here. There's tree balancing algorithms which allow you to get the tree that's kind of like level-ish, you know, where one side isn't any more than like 1 level deeper than the other side, which should give you on average better search performance.
Like, the basic idea, like the heuristic.
Yep.
So for applying possible, for searching like path, you try like to focus on the, in the path to be getting your goal state. So
Your goal state being to find the value you're looking for.
yeah.
Okay.
Like for example, 8 puzzles. As examples for.
Sure, but with the understanding that by keeping your tree balanced, the goal is to have your average search be fastest. Not necessarily that every search is the fastest it could have been, but that your average search is fast. That make sense?
So yeah, like
You could have a scenario where the unbalanced tree actually gives you the fastest search result.
like getting a true state with is the smallest heuristic path, which is from which the goal might apparently be reached with the least cost. So that's kind of the binary tree you're looking for, especially if we are dealing with it like depth first.
Well, if you're trying to guarantee least cost, you probably would use a different kind of tree. You'd probably use something called an AVL tree. AVL trees are self-balancing trees. It's like a binary tree, but kind of a binary tree on steroids. If you're always looking for the most efficient cost to an individual search, you need to make sure your tree is optimally balanced, not just balanced from a left-heavy, right-heavy side. So you actually rotate across root nodes for that.
I have to deal with the data. I mean, sometimes, for example, if I get like, let's imagine I have the phi was 0, 1, 2, 3, 4, 5, 6, 7. Then it will be, you know, the path is going to be right or left, depends the number of pin enter first. So where's the balance? How can I make the balance from that?
Talk that over with Professor Wall so we can go home.
Well, that's the advantage of an AVL tree, is that what you have is your root node is almost always the median value, or close to it. So then you have, on average, end performance to any node for searching for any individual node. Using just a generic binary tree, especially for not balancing at all, it's a crapshoot. Yeah, I mean, what we just wrote today doesn't do anything in terms of guaranteeing reasonable performance. All it guarantees is that the stuff is stored in sorted order. It might be horrifically inefficiently stored, but it's stored in order. Make sense?
Yeah.
That's all we've written up to this point. Next week, I'm going to have you look at balancing tricks that will allow it to be stored at least in a little bit more not left or right heavy way. But it's still not quite AVL trees, even at that point.
So, as a result, the following four will be to become as impractical as representing the whole graphics of the binary tree. Will be a huge if you couldn't get in the goals you are looking for.
If you had to search the whole tree?
Yeah.
Well, I mean, depending on how big the list is, yes. A binary tree is no different than a normal binary search on an array. You know, sometimes it's called a dictionary search. So if you took a dictionary and let's say you were looking for my last name, so you were looking for Lippman, you'd open the dictionary to roughly the center. Put your finger in there and say, is that the answer? No. Should Lippman come before or after? Let's say it comes to the left. You rip the phone book in half, throw out the right half, don't need that anymore. Go to the center of the left half. Is that my name? Decide which side, keep doing that over and over and over again. That's how binary trees work. Okay, so binary trees really are a data structure representation of a phone book. But the idea is that with some additional balancing, we can actually improve performance of searching them over and above the open to the center, guess. Open to the center, guess. We can increase the performance with a tree. Make sense? All right, quickly, let's just look at the report real quick, just so you know what I've asked you to do. So, write a 2 to 3 page paper discussing common uses for binary trees. Describe at least one case study which describes a project that uses binary trees in terms of why it uses binary trees and how it uses them. So, for instance, if you'd like to pick Oracle, you can, but I want you to tell me how does Oracle utilize binary trees and why did it choose to do that? Make sense? There'll be lots of examples of case studies that use binary trees. All right, and then as we decided, we will not meet in person next week because of Thanksgiving break, but you will have a homework assignment, and I'll probably give you some articles or something to read to help you do that homework assignment, but we won't actually meet in class. Sound good? Questions, comments, concerns, bribes? All right, I'll put the code up and I'll unlock the homework assignments, and I'll see everybody in 2 weeks.